So, hello everyone again. This is lecture 2 part 2 of alternating current. In the previous part of this lecture only we have started with a discussion regarding the AC voltage applied to an inductor. We have derived everything which is of required sequence except for instantaneous power. We understood what is basically inductive reactance, why it is being said as analogous to reactance or basically a resistor and so on. Today we will start the discussion regarding the use of phasor diagrams in this concept, and then we can move forward with the instantaneous power and then finally to the new chapter new concept regarding AC voltage applied to a capacitor. So, that thing being said, this is lecture 2 part 2 of alternating current. I am Sameer Lavankar. Let us begin our discussion. So, a course outline for you. Currently we are on the fourth topic, that is regarding the AC voltage applied to an inductor. So, these all things are already being done. We have understood the concepts of introduction, as in why are AC sources required as in front of your DC sources, what is the basic voltage and current scenario when AC voltage is applied to a resistor, the use of phasor diagrams, and now we will do the application of phasor diagrams in the case of AC voltage applied to an inductor and then to capacitor and series LCR circuit. So, let us begin the discussion we left in the last lecture. So, we finally obtained what was the value of I was basically equal to Im sin omega t minus pi by 2, and we denoted that what is omega L is basically called as your inductive reactance. Okay, fine. So, now till this point we have already been completed. Now, let us move to the next point. So, figure A shows the voltage and the current phasors in the present case at instant t1, at any instant. So, for example, to understand this scenario we are trying to understand what will happen at some time t is equal to t1. Okay. So, let us suppose that this is the voltage being occurring here. If this is the voltage being occurring here for lagging behind concept. So, let us say you can understand this concept as sign convention also, or you can understand this in the case of scenario of saying lagging or being ahead. Okay. So, whenever the concept of lag comes into picture or whenever the word lags comes into picture, whenever it is said that the current lags or as in x thing lags the y, then always the value of or the word which is being said in the starting is downwards or it is in the clockwise sequence. Okay. To understand this through an example, it is being said that current lags the voltage by pi by 2. The first word is current, the second word is voltage. So, what you will basically do? We will either first make the second one, we will do a clockwise sequence and then we can make the value of I, or in another case sequence what we can do? We can make let us suppose current first and then we can go in anti-clockwise sequence and make voltage. So, that is how the concept of lagging or going ahead comes into picture. In the another case scenario which will happen in basically capacitor, the current will not lag, voltage will lag the current. So, again what we will do? We will just make capital V here and we will make capital I. So, that is how. So, you can basically understand this as sign convention also, or you can basically understand by logic also, as in the current is lagging, correct. So, if current is lagging and the movement in which you are trying to make the circle is basically in this form, that means that the current will make that circle after voltage. If you see logic wise, voltage is some sort of here. What will voltage do at some time t is equal to t2? It will go here, then it will go here, then it will go here and so on. But as current is lagging behind, that means this circle being formed by current will be after it is being formed by voltage. That means it will start at some point which is before voltage. If we are going in anti-clockwise sequence, then it is by logic it is quite evident that we have to start the value of current I at some angle which is in the clockwise sequence from voltage. So, by logic sequence also you can go, or you can just remember the sign convention, as in if the current is lagging the voltage. So, just try to make voltage at some higher and then try to go clockwise to find the value of or to find the phasor diagram for current. Okay. So, that was a logic or basically sign convention, as in how we draw the diagrams. Now, for similar case scenario, if we now try to find the waveform for or the oscillatory waveform for this both. So, what we will do? Let us say we are trying to find the position of this phasor diagram into reality or basically how it is in the sinusoidal waveform. What we will do? We will basically draw horizontal line, correct, at some time t1. So, this time t1 is already known. So, we will just draw vertical line again. The point at this will meet will be at some time t1 what is the value of voltage. Similarly, for current also what we can do, we can draw a horizontal line like this, we can draw a vertical line again like this, and so this is the point or the value of the current at some time t1. Okay. So, that thing being said, I think it is now clear as in how the diagram, both diagrams are being made. Okay. So, you can either go from this to this also, or you can either go from this to this also. General case scenario, it is quite easy to understand the phasor diagrams, and then we can directly move on to making our actual waveform diagrams. Fine. So, figure A shows the voltage and the current phasors in the present case at some instant t1. So, please remember it is at some instant t2. What if I say that you try to make the same diagram at some time t2, which is where t2 is greater than t1, what you will do? So, basically let us say if this is the voltage at some time t2, then this some sort of here will be the current I. Okay. So, that is how you can make the same diagram at some time omega, at some time t is equal to t2, where t2 is greater than t1. Okay. Again, next thing is the angle between this, I also explained when we were trying to understand AC phasor diagrams. So, the angle between this, that is capital V and capital I, is nothing but your phase angle. Okay. Quick revision only, nothing new. So, the current phasor I is pi by 2 behind the voltage phasor capital V. What is the phase angle? This is the phase angle required in this sequence. So, this is the phase angle. Okay. So, because the phase angle is pi by 2 and it is minus pi by 2 basically. So, what we will do? We will basically say that this is equal to nothing but pi by 2. Okay. So, the current phasor I is pi by 2 behind the voltage phasor V. Okay. So, what is the ahead position V? Ahead is this case scenario if you are going in this sequence, and behind as in it is back. Okay. So, if it is back, then we can say that capital I is basically pi by 2 behind the voltage V phasor. Okay. Next thing is, when rotated with frequency omega counterclockwise, they generate the voltage and current as shown in the figure B. Okay. So, whenever you try to go in this sequence, this diagram comes into picture. Similarly, this diagram comes into picture. Okay. In another case scenario also, when we were trying to understand these all concepts, when we were trying to derive the value of current, we obtain the value of current as cos omega t into some function I m, correct. So, you can see clearly this is the waveform of sine and this is the waveform of cos. Only the value of amplitude is referring, because for the value of amplitude was Vm for voltage and it is Vm by omega L for current. So, because it is slightly lower, the value of amplitude was coming out to be slightly less as compared to V. Okay. So, that thing is explained also, that when it is rotated with frequency omega counterclockwise as in this case scenario, they generate the voltage and current as shown in the figure B. Okay. So, this is how it is being obtained. Okay. Next thing is, we see that current reaches its maximum value later than the voltage by 1/4 of the period. Okay. So, as you can see here that this was the point at which our voltage reached the maximum value and this was the point at which the current reached its maximum value. The difference between this time, or the difference between the time frame at which both of these reach their maximum value, is nothing but equal to pi by 2. Okay. That is only written here. So, we see that the current reaches its maximum value later than the voltage by 1/4 of the period, that is pi by 2 by omega. Okay. Okay. So, it is in the term of omega t. So, it will do pi by 2 by omega here. Okay. Fine. So, basically it was time required, we are trying in terms of time. Okay. Next thing is, you have seen that an inductor has reactance that limits current like resistance in DC circuit. Does it also consume power like a resistance? Let us try to find out. So, now let us try to calculate the value of instantaneous power in this case scenario. Okay. So, let me start in this page only. Okay. So, now the instantaneous power, similar case scenario as in we try to do for AC voltage applied to a resistor. Now, we will try to understand the AC voltage applied to an inductor. So, the instantaneous power supplied to the inductor is, okay. So, how we will calculate power? Let me denote the power for this inductor as P with a subscript L. What is normal equation for power? Power is I into V. So, I into V. correct. That is nothing but equal to, what is the value of I we obtained? We obtained the value of I is nothing but Im sine of omega t minus pi by 2, and what is the value of Vm? Vm was originally assumed as equal to Vm sine omega t, correct. So, we can basically write this equation as nothing but equal to, so in the place of sine omega t minus pi by 2 we can also write minus cos omega t. So, it is minus Im Vm sine of omega t into cos of omega t, correct. Now, again trigonometry, so just multiply and divide by 2, we will get the answer as nothing but equal to minus Im Vm by 2 into sine of 2 omega t. Okay. So, normal trigonometry is being involved, 2 sin omega t cos omega t is nothing but equal to sine of 2 omega t. Okay. Now, we will try to calculate. So, this was the instantaneous power being supplied. Now, let us try to calculate the average power over a complete cycle. Okay. So, basically average power over a complete cycle is, how to calculate it? It is basically, let me note that capital average power as capital P L. So, it is nothing but, this is the denotion. So, it is Im Vm by 2 into sine 2 omega t, correct. So, we know that Im Vm and 2 are constant. So, we can directly remove them out of this scenario. So, it is minus Im Vm by 2 into sine of 2 omega t. Now, when we are trying to understand the same concept for AC voltage applied to a resistor, we know that average over a some complete cycle for sin n omega t or cos n omega t is always 0. Therefore, this is nothing but equal to 0, as sin of 2 omega t is equal to 0. Okay. So, that is the next concept. So, basically what we obtained that the average power supplied to an inductor over one complete cycle is 0, but please remember, instantaneous power supplied to the inductor is always having some value, that value is minus Im Vm by 2 into sin 2 omega t, but the average power over a complete cycle, we are just trying to understand this for a one complete cycle, average power over a one complete cycle is always 0. Okay. So, that is how this concept is being explained here. Okay. Fine. So, that thing being said, now let us try to solve one of the example and then we can move on to the next concept regarding AC voltage supplied to a capacitor. Okay. So, please understand this question clearly. So, a pure inductor of 25 millihenry is connected to a source of 220 volts. So, basically voltage is given to you and inductor capital L is given to you. First question is find the inductive reactance, second question is find the RMS current in the circuit if the frequency of the source is 50 hertz. Okay. So, what all things are given to you? Let me just write first of all. So, capital L is given to you as 25 millihenry, voltage capital V is given to you as 220 volts, okay, and next thing is given to you as this F, or we can write it as nu. So, nu can be written as nothing but 50 hertz. Okay. So, first of all the question is find the value of inductive reactance, simple formula, inductive reactance is nothing but equal to omega into L, omega is nothing but 2 pi nu into L, value of 2 is known to you, pi is known to you, nu is given as 50 hertz, capital is given to you as 25 millihenry, simple calculations, finally you will obtain the value of inductive reactance is nothing but 7.85 ohms. Okay. So, you know the value of XL, you know the value of V, right. Next question is find the value of RMS current in the circuit. How to calculate the value of capital RMS current in the circuit? It is simple, its capital I is equal to capital V by XL. Okay, no root 2, no divide by 2, nothing of that sort, just simple capital V by XL will give you the value of RMS current. Please remember this sequence, people do confusion in this concepts. So, whenever the value of RMS current is asked, directly calculate the value of capital I is nothing but equal to capital V by XL. If the value of peak current is asked, then you may need to multiply it by root 2 or let us say divide by root 2 depending upon the sequence or questions being asked. But for this question, if RMS current is asked, you know the value of supply voltage, that is capital V. If you know the value of reactance or the resistor, in the case of resistor it is resistor only, just divide capital V by XL and you will obtain the value of current. So, in this case scenario it is nothing but 220 volts upon 7.85 ohms which we just obtained, and therefore, this value of current is nothing but equal to 28 amperes. Okay. So, that was a simple question regarding the inductor. That thing being said, now let us try to understand the next concept, that is AC voltage applied to a capacitor. Okay. So, we have completed with AC voltage applied to a resistor, we have completed with AC voltage applied to a capacitor inductor. Now, let us understand AC voltage applied to a capacitor. Okay. Same case scenario, just in the place of resistor or an inductor, a capacitor is being added upon now. Okay. So, figure shows an AC source epsilon generating AC voltage V is equal to Vm sin omega t connected to a capacitor only, a purely capacitive AC circuit. What does it mean? It basically means it is a assumption that the internal resistances in the wires is 0 and there is no external resistance, no resistance is even not there, only and only a capacitor is being involved apart from a EMF voltage being supplied, which is written in the form of V, which is equal to Vm sin omega t. Okay. So, when a capacitor is connected to a voltage source in a DC circuit, current will flow for a short time required to charge the capacitor. So, what actually happens in a DC circuit? So, let us suppose this is a DC circuit, this is the EMF, this is the capacitor. Now, the current keeps on passing, that means the charges keeps on accumulating on the two sides of the capacitor. Once the charges are being captured or being the capacitor is fully charged, it limits or stops or restricts the current passing through the circuit or passing through it, and if once this happens, then the current passing through the circuit will be equal to 0. Okay. So, when a capacitor, so these all concepts are already been explained in the chapters of electrical charges and so on. So, I will not go into that detailing now, just simple revision was being done here. So, when a capacitor is connected to a voltage source in a DC circuit, current will flow for the short time required to charge the capacitor. As charge accumulates on the capacitor plate, the voltage across them increases, which opposes the current. So, because voltage keeps on increasing, so it tries to oppose the current. That is, a capacitor in a DC circuit will limit or oppose the current as it charges. Okay. So, simple explanation which I just gave. So, basically charges keeps on accumulating on the two plates of the capacitor, and hence when the charges keeps on accumulating, there exists a point at which the complete charging of the capacitor is being done, and therefore, no current is passed through the circuit further. Okay. So, next thing is, when the capacitor is fully charged, the current in the circuit falls to 0. When the capacitor is connected to an AC source. So, now what happens in an AC source? When the capacitor is connected to an AC source, as in the figure, it limits or regulates the current, but does not completely prevent the flow of charge. Because it is a sinusoidal waveform, the reason of this sinusoidal waveform leads to either regulating the current or basically limiting the current. No current is never a case scenario in the case of AC voltage applied to a capacitor, ideal capacitor. Okay. The capacitor is alternately charged and discharged as the current reverses each half of the cycle. Okay. So, that thing being said, that was a basic discussion or basic introduction of AC voltage applied to a capacitor. Let me stop it here. In the next class, we will start with the understanding of instantaneous voltage. Again, we will try to understand the value of current and so on, and then we can move forward with the power of these all concepts regarding capacitor, and then we can move on to the next concept regarding series LCR circuit. So, that thing being said, let me stop the discussion here only. So, thank you so much.